Oh, hi everybody. Welcome back to my chemical principles lecture. We're on lecture number 743. Listen, this is about the time we're kind of in the muckety muck at this point. We talked about atomic structure. We started off with a periodic chart, unless you're a librarian, in which case it's the periodical chart. We talked about chemical reactions, and now we're talking about a lot of details, and this is where students tend to kind of drift away. So I hope you're keeping up with me. We're talking about gases and liquids today. The next chapter is solutions, which is something that is very, very important, especially if you are in the medical field. Talking about concentrations and different kinds of concentration units and why we choose what we choose. Some of them are easy to do, to put together. Some of them are easier in calculations. We're going to talk about the differences between the two. It is a chilly, chilly day here. And we have that little skull down there in the glass jar. Of course, my cat Star, who is a black cat, is represented down below. And that fella in the scar is Napoleon. Not the Napoleon, but a Napoleon. We call him Napoleon because Bonaparte tried very hard to get Kim to spit on that one. Okay, should we get started, or is this nonsense just too much fun? Compose yourself, Kim. All right. Let's do at least one, maybe two or three calculations here. It all depends on how many you want to do. I'm not expecting you to do these calculations yourself. Like I say, homework, you choose what you want to do for homework. It's up to you. It's no big deal. We're not having a quiz. We're not having an exam. We're just trying to learn. But like I say, when I teach this class, what I have in mind is the parent who is trying to help their child through their homework. And if your child is taking chemistry, your child is going to be doing calculations. So you may not remember this, tomorrow. But I hope that you remember that you've seen it, and I hope that it comes back to you. And YouTube being YouTube, it'll be up on YouTube apparently forever. So you can always come back and review it should you choose. I don't even know what lecture we're on. This is like lecture 13, I think. I'm not sure. All right. So let's do a real world example, because, the thing is, and this is where students tend to forget, we start talking about theories and details like this, and people forget. Chemistry is all based on experience. These gas laws were all observed in the laboratory. That's how they came out to be gas laws. It's pretty cold out. So suppose we blew up our tires when it was pretty warm outside. We blew them up to 35 psi. When the temperature was pretty hot day, 23 degrees Fahrenheit. 23 degrees Celsius. What will be the pressure today, when the temperature is about 6 degrees below zero. The gas is about 6 degrees below zero. Now, here's the question. Here's the first question I'm going to ask you. Do we need to derive a new law, or can we just plug everything into the ideal gas law and figure it out from the ideal gas law? The clue is in the question. If you have changing parameters, then you need a new relationship. Okay? If you are given the ideal gas law, remember, you have pressure, volume, amount of gas. There. You have pressure, volume, number of moles of gas. That's the amount of gas, and you have the temperature. So there are 4 parameters. In a straightforward ideal gas law calculation, you will almost always be given 3 of them, and you'll be asked to find the 4th. This one, notice, we are only given, well, first of all, you can be given 4 parameters, but the big clue here is that you have changing parameters. If one of those parameters changes, like here, we have temperature changing, we have pressure changing. If you have a changing parameter, you need to derive a new gas law. What gas law do you need? Well, it doesn't matter, because we're still going to start off with the ideal gas law. But in order to derive the gas law that we need, we're going to get the parameters that we need on one side of the equation. I always get it on the left side of the equation. So we don't need volume. So let's get rid of volume here. And of course, we can do that provided we divide both sides. That's simple algebraic law. Anything you do to one side is fine as long as you do the same thing to the other, with exceptions. And we need to move the temperature. For the temperature's on right now the right side of the equation. We need it on the left side. So we've gotten rid of volume here. Let's move the temperature over. Like this. Which gives us our new law. Now keep in mind, number of moles, the gas constant, volume. All 3 of these are constant. We may not know what that constant is, but we know it's a constant. And if we change things from pressure 1 and volume 1 to temperature 1 and temperature 2, this is the same constant for both. So now we can just write our new gas law and add subscripts. And this does turn out to be a ratio. So this is the gas law we have. And I don't know that this gas law even has a name. As I recall, Charles, or Chuck's law, as they're known, uses volume, not pressure. So I don't even know if this relationship has a name. Now, I've told you this before, and I'm going to drill this into you. There are 2 cardinal rules for doing gas law calculations. You must remember the cardinal rules. First rule, you must have consistent units. Now, here we have PSI. Do we need to convert that? I mean, after all, our constant for R is atmospheres. So do we need to convert from PSI to atmospheres? No. As long as we're consistent. As long as we're happy with PSI as the unit in our final answer here, we can keep it PSI. It doesn't have to be atmospheres. So let's just keep that as atmospheres, which is a good thing because frankly, off the top of my head, I don't know if I remember the conversion factor from PSI to atmospheres. I'd have to look it up. Not that it's not available. Now, fortunately, we are in degrees Celsius here and here, so that's okay, right? Wrong. Because the second cardinal rule, we must use an absolute temperature scale. For us, it's Kelvin. And this is why exactly. It's this negative sign right here. If we put a negative sign here, we're going to get a negative pressure. That's nonsensical. That doesn't work. We must convert to an absolute temperature scale so we never, ever, ever go through zero. We can use any absolute temperature scale we want, but the one we will use in this class is Kelvin. And to convert from Celsius to Kelvin, just add 273.15 if you need the 0.15. We do not need 273, son, not 275. I'm a little tired today. We don't need the 0.15 because we don't have decimals in our temperatures. So, and again, we're going to increase the number of significant figures by doing this. That is okay. When you add or subtract, you can increase or even decrease the number of significant figures. Did I do that right? Let's see, 267 plus 6 is 273. That is correct. Now it's just plug and chug. We have 35 psi. It was 35 psi at 296 Kelvin. What is our new pressure at 267 Kelvin? A little bit of algebra and manipulation. And if you have trouble with this kind of algebraic manipulation, I'm more than happy to help you. Let me know that you need help. We will arrange a special tutoring session on how to do these calculations. Happy to do it. But in the meantime, what just binged on me? And let's see here, we have 2 sig figs. So the pressure will drop to 32 psi. We will lose 3 psi. I'm getting 31.6, which rounds to 32. My chair keeps drifting on me, so I keep moving a little bit left. And it just feels weird. (32 psi). Okay. Any questions about that example? Would you like to see a straightforward ideal gas law example? Let's do a straightforward ideal gas law example. Sometimes it will look like you are not given enough information. when I was teaching, when I was the director of a forensic science lab back in Vapid City, I had a high school contact me. They had a team that they wanted to send to a forensic science challenge, kind of a camp. And it was the first time they've ever participated. And they wanted to know if they could get a little training on how to be successful. So they showed up. And I trained them up in their very first year, and they were cheated, honestly, because they were supposed to go to the crime scene and they were supposed to be given, I think, 10 or 15 minutes at the crime scene, as well as the dialogue, to examine and look for clues and whatnot. And they were falling behind. So this particular team was only given about 2 minutes. We're not given enough time. And with that handicap, they still came in second their very first year. How did they do that? Well, the problem is that we see things that we don't understand. We tend to gloss over them. We tend to ignore them. And I got them in the habit of looking at every word in the description, every word, and make sure that they understand what every word means. So I'm going to say this out loud, and then we're going to write down the given. What is the volume of 1 mole of gas at STP? So what do we have? We're looking for the volume of 1 mole of gas at STP. Is that enough information? Because we have 4 parameters. We have temperature, pressure, volume, and number of moles. All we have here is number of moles and volume. Students tend to gloss over the term STP. STP stands for standard temperature and pressure. Standard temperature and pressure. This is chemist shorthand. In a real quick and easy way, just to make sure that I'm doing this correctly. Ooh, I was wrong. Okay, that's fine. Sometimes I forget too. It's been a while. Okay. Standard temperature is always taken to be 273 Kelvin. Freezing point of water, 0 degrees Celsius, 32 degrees Fahrenheit, 273 Kelvin. So when I say STP, we know temperature. The temperature is 273 Kelvin. And the standard pressure is the pressure my students feel when they're doing their homework. It's like a joke. This is smaller. Standard pressure is 1 atmosphere of pressure. It's the average pressure at sea level without a pressure system coming through. So when I say at STP, we do know pressure and we do know temperature. So now, look, I have temperature, pressure, volume, standard temperature, pressure, moles of gas. The only thing we don't know is volume. So we know 3 of the 4. So it just becomes, and look, we are already in Kelvin. There are 2 ways to make sure that you have that you have consistent units. One is to convert everything to one particular value of R. Remember, R changes depending on the units. So either convert your pressure, your volume, or temperature into those units, or find a value of R that has the units that you are using. It's easier to remember one value for R. Much easier to remember just one value for R. So that's what we do. And that value of R, if you recall, I gave this to you once before. Let's see, I only need 3 sig figs. It's 0.08206, but we only need 3 sig figs. So let's say it's 0.0821 liter atmosphere per mole Kelvin. We're at moles, we're at Kelvin, we're at atmospheres. All this tells us is that our final units for pressure is going, for volume is going to be liters. So plug and play. Son of a mutated Baghdad roundworm. Okay. So we have 1 atmosphere of pressure. We are looking for the volume. We have 1 mole of gas. Or constant 0.0821 liter atmosphere per mole Kelvin. Is that you or me? At 273 Kelvin. Excuse me. I sneezed, so suddenly my nose is running. Or, now notice atmospheres will cancel. They're both in the numerator. Moles will cancel. Kelvin will cancel. What are we left with? We're left with liters. And if we set this up correctly, just punch it in your calculator. 0.821 times 1 times 273 divided by 1. $22.4 liters. Now, I wanted to do this example, frankly, because some chemistry teachers have students memorize this constant. 1 liter of gas is 1 mole of gas is 22.4 liters. They use it in stoichiometry calculations. Oh, that's a good thing we can do. That's a good thing we can do. Let's do that. Anyway, they have their students memorize this because anytime they need to convert from volume of gas to moles or vice versa, what's 22.4 liters per mole, right? Right? Wrong. It is 22.4 moles per liter only under one very specific set of conditions, namely STP. If you are running your gas law, if you're running stoichiometry at 0 degrees Celsius or the freezing point of water, Yes, it's 22.4 liters per mole, but what's the point? Most of the time we're at room temperature. So why memorize that? It doesn't make sense to me. I mean, it's, you know. Let's do we have time. Let's combine some things. Here's an interesting problem. Suppose we eat an antacid. The active ingredient in an antacid is typically, not always, calcium carbonate. And it neutralizes stomach acid. Let's go back and review. What's the charge of calcium? How do we find it? Charge of calcium is on the periodic chart. Unless you're a librarian, then it's on the periodical chart. Calcium is an alkali earth metal, which means calcium, I'm going to give myself a little bit of room here, is a +2 charge. Carbonate. I asked you to memorize some polyatomic ions. If you did, you would recognize that carbonate is -2. So you have calcium carbonate. But we have a common denominator. So this is the correct formula for calcium carbonate. Now, when calcium carbonate reacts with hydrochloric acid, we will get calcium chloride. Water. And carbon dioxide, which is a gas, unless you're Mick Jagger, in which case it's a gas, gas, gas. Before we can balance the equation, and this is so important, before we can do stoichiometry, we need a balanced chemical equation. Before we can balance the chemical equation, we must figure out the products. We must figure out all of the compounds. We know that CO2 is carbon dioxide. That's right. We know water is H2O. That's right. Is calcium chloride correct? Well, we just pointed out calcium is +2. Chlorine, if you look on the periodical chart, is -1. Chlorine is a halogen, so it is always a -1 charge. So we do our cross trick and we see the correct formula for calcium chloride must be CaCl2. We do not have a common denominator, so we need to put this up here first. That's the proper formula for calcium chloride. So we have 1 calcium on the reactant side, 1 on the product side. We have no elements, so there's nothing we can really just save. We have 1 carbon on the reactant side. We have 1 carbon on the product side. We're not going to balance the oxygens because look, oxygen is in 2 different locations over here. And that's bad, okay? because if oxygen is off, we won't know which one to balance. So let's save the oxygen. We have one hydrogen on this side. Ooh, we have two hydrogens here. That does not change the calcium or the carbon, but we can put a 2 here to get two hydrogens on this side, two hydrogens on this side. Now let's just make sure the oxygen is truly balanced. If the oxygen is not balanced, we did something wrong. Go back and double check the compounds, make sure that these compounds are correct. But we have 3 oxygens on the reactant side. We have 1 oxygen on the product side in water and 2 more carbon dioxide. 1 plus 2 gives us 3. This is a balanced chemical equation. I'm not quite sure how many grams of calcium carbonate is in a Tums tablet. So let's assume that we have 1 gram of calcium carbonate. Calcium carbonate, when it reacts with their stomach acid, is going to make us belch. We're going to belch because we're giving off gas. How many milliliters of gas are we giving off in our reaction here? How many milliliters of gas are in that burp? And men, remember, the louder belching is a mating call. So the louder you belch, the more impressed the women around you are going to be. So make sure that you belch loudly with your mouth open. Okay. I almost got through that with a serious tone. All right. If you recall the most famous reindeer of all, the steps to stoichiometry. First step, convert whatever you're given. Now notice when I do a stoichiometry problem, I just put a question mark where I'm trying to figure out. I'm trying to figure out the carbon dioxide. So I put a question mark there. That's my endpoint. It's my little reminder is my endpoint. So the first step, whatever you're given, which in this case is calcium carbonate, you're going to need to convert that to moles. Well, we have a mass here. Do you remember how to convert mass to moles? With the molecular formula, with molecular mass. So we're going to need molecular mass of calcium carbonate. So the first step, convert whatever you're given to moles. Second step is the mole-to-mole ratio to give you the moles, not of what you're given, but to get to the moles of what you want. The third step is to convert whatever moles you have to the final units that you want. So convert units to moles, mole to mole, mole to units. It's a nice symmetry there. So we know we're going to need the formula mass of calcium carbonate. Calcium, as I recall, is 40.08 grams per mole. Is that correct? This is why I don't have students memorize a periodic chart. Even if you remember it, you're going to double check. So I memorize. Let's see. Calcium is indeed 40.08 grams per mole. Remember those numbers on the periodic chart? Always add the units grams per mole. Carbon is 12.01. Oxygen is 16. So we have 1 for calcium carbonate. We have 1 calcium at 40.08 grams per mole. We have 1 carbon at 12.01 grams per mole. And we have 3 oxygens at 16 grams per mole. Where's my calculator? So we have 40.08. This is a good one to practice on your calculator, because I know how my calculator works. So I just got a weird answer. That can't be right. Let's do it again. That's better. When you do a calculation, always look at the number that you get and make sure that it makes sense. I got a 0.01 at the end there, and I know you had 0.08 to 0.01. It should have been a 0.09 in the end. So what I got on my calculator could not have been correct. Now we are ready to set up, and as I recall, Kim likes it this way. And whenever Kim gets me. Sorry, I couldn't resist that. She's my only student. I'm being so mean to her. I apologize. Whoa. I would not be teasing her if we were not such good friends. Remember to look at where the units are. Gram is in the numerator, so we need gram in the denominator. Keep the number with the unit. It is 40.08 grams per 1 mole. Remember, 1 is always assumed. Well, we need the grams on the bottom. First step in stoichiometry, get from whatever units you're given to moles. Second step is the mole-to-mole ratio. We're at moles of calcium carbonate. We want moles of carbon dioxide. Well, notice that this is just a 1-to-1 molar ratio. But again, calcium carbonate in the numerator, so we need calcium carbonate in the denominator. Now, this is where students who memorize that constant, 22.4 liters, is going to mess up. Because this, oh, I forgot to give you the rest of the parameters. How many milliliters at room temperature, which is 20 degrees Celsius. This is not at STP. This is room temperature, which is roughly 20 degrees Celsius. So how do you handle this? Well, notice that here we're going to need a gas law calculation. So at this point, we're going to stop at moles instead of continuing, because usually I'll continue on to the final units. But gas laws, stop at moles. Stop right there at moles. So we know moles of CO2. If we do that, and let's say 1 atmosphere of pressure. Forgot I'm going to need those as well. So we need pressure. We have temperature. We're looking for volume. This will give us moles. That's the third of the 4. So we're going to stop at moles here, and let's see what we get. Well, this is going to be, oops, I did that wrong. Is it 40.08? Kim's letting me get away with it. It's not 40.08. That's for calcium alone. We have 100.09. So let me get away with that. And let's say, by the way, let's say it's not 1 gram. Let's say it's 1.00 grams for significant figures. Which makes sense. We're very close to 0.01 moles because calcium carbonate is very close to being 100 grams per mole. So that makes sense. Now we have moles. Notice a couple of things here. First of all, we're at the wrong temperature because we are the second cardinal rule. Always use an absolute temperature scale. So we need Kelvin. Wow, son, wake up a little bit. Now we have milliliters here. Our constant for R is in liters. So notice we're going to have the wrong units. But we're going to leave that for now. So our gas law, Pivnert, we have 1 atmosphere of pressure. We are looking for the volume. We have 0.00999 moles of gas, 0.0821 liter atmosphere per mole Kelvin times 273 Kelvin. To 93 Kelvin. 273, 293 Kelvin. So 1 atmosphere times volume is equal to 0.0999 moles. I don't like doing this in 2 steps. So let's redo this. We have 1 atmosphere. We're looking for volume. 0.00999 moles of gas, 0.0821 liter atmosphere per mole Kelvin at 293 Kelvin. Do the algebra. And we get 0.240 liters. If I did that correctly. But notice that this is the wrong volume. This is liters. We need milliliters. Well, remember, there are 1,000 milliliters in 1 liter. This is 200. Wow. That belch has a volume of 240 milliliters. That's a lot of gas. I mean, let's put that in perspective. This is 500 milliliters when it's full. It's about half drunk. You're getting that much gas out of your mouth. And that's assuming it's 1 gram of calcium carbonate. So that's a lot of pressure. Okay, let's take a break. It is roughly 10:45. Let's take a 5-minute break. I'll see you back here at 10:50. Go and have a calcium carbonate and have a good. Okay, welcome back. I'm having a little bit of fun shuffling images around on my screen. It is the haunting season. My cat actually wrote today's blog. So embarrassing when my cat writes my blog for me. Okay, we can do another calculation if you want, but I just want to point something out here. We've been doing ratios of 2 of these. We can also do ratio of 3 or 4. It's very simple. Suppose we want to know the relationship of changing. How does the temperature change if pressure and volume change? So now we have 3 parameters instead of just 2. Well, we're going to do it exactly the same way. This is called the combined gas law. It's the same thing. And we can do an example, but you'd be given 2 different pressures, 2 different volumes, and 1 temperature, you'll be asked to find the other, or 1 pressure, you'll be asked to find the other. You'll be given 5 of the 6, and you just solve the 6th. My favorite thing to do on exams, oh, I'm not sharing my screen. Ha! So we'll do it again. My favorite thing to do on exams was to give students gas laws for which there is no name. So this is the combined gas law. What if you're changing pressure, volume, and number of moles? No, let's keep volume constant. Let's say we're changing pressure, temperature, and number of moles. Well, we're not going to need volume. So divide both sides by volume to cancel on this side. Divide both sides by temperature to move this temperature, and what we get is, oh, we also need to divide both sides by the number of moles because we're changing the number of moles. So we cancel that on this side. Let's do that again from scratch because I feel like I kind of mucked it up. Do it again. So we're given some set of parameters, P1. We're given an initial pressure, temperature, number of moles. And we're trying to convert it to a new temperature and pressure. We're trying to find the number of moles. Remember, all we need to do is get all of the unknowns on the left side and everything that's known on the right. So we know, for example, volume does not show up in our problem. So we can get rid of volume on the left side. We need to move the number of moles. And we need to move the temperature. So our relationship becomes this. Given a problem, you just plug in everything that you know. You solve for the one that you don't. So it's pretty straightforward. You know what? I think I know why I'm binging, and it's because of this bad boy right here. Let's close that. All right. So now here's a whole new relationship that does not have a name. This is Blyle's gas law. Nah, it doesn't need a name. I'm full of enough gas anyway. So it doesn't have to be just 2 parameters. It can be 3 parameters. Heck, we can solve for all 4. PV over NT, P1D1 over N1T1 equal P2V2 over N2T2. It could be anything you want. Doesn't matter. But everything you need, get it on the left side of the equation. Everything you don't need, get it on the right side. And whatever's left on the left side, that's your gas law. Just add your subscripts 1 and 2. Pretty straightforward. I thought I just closed that. Close. For crying out loud, why are you not closing? There we go. Okay. Now, any questions about gases and gas laws and all that fun stuff? Every day, every morning, first thing I do when I get out of bed is I go and feed all of my guests, which is kind of embarrassing because I do it before I put on any clothes. But when I say I feed my guests, I have something, I'm assuming I have a couple stray cats. So I put out a handful of cat food on the back porch. And to entertain my cat, I put bird seed on my, sort of by the window on the side of the house, bird seed and peanuts. And I put peanuts out for Jerry, who lives under my back deck. Jerry is a groundhog. I call it Jerry because I don't know if it's Jeri or Jerry. I don't know if it's a male or female, so it's Jerry. Then I put out a handful of peanuts on my front porch because something's been eating them. I have no idea what. Heck, it could be George for all I know. Then I go and I put water in the bird bath. It's supposed to be a bird bath. Of course, when it's really hot, the birds drink it. And for some reason, they drop peanuts in the bird bath. I don't know why. It's very strange. It is a chilly, chilly, chilly day here today. This morning was cold. In the water was not water. The water that was left in the bird bath from yesterday was ice. Cold, cold, cold here today. So what makes ice? Why did that liquid turn to solid? Why does water as a gas, unless you're Mick Jagger, in which case it's a gas, gas, gas. And if you don't look up that song, Jumpin' Jack Flash, you're never going to get that joke. Why does it convert to liquid? Every single compound, every single element has been liquefied at one point or another. Liquid helium liquefies at 4 Kelvin. Helium is the most ideal gas of all of the gases. It is the smallest gas. It is the smallest atom, which makes it as close to a point particle as you can get. It has the absolute weakest intermolecular forces. So it's very hard to get it to liquefy, but it does, which means there's something holding the liquids together. Now, helium, by the way, everything else known to chemistry has been solidified. Helium is the only thing that has never gotten cold enough to actually form a solid. Very unusual. But it does form a liquid. And to say it's a liquid means there's something that has to be holding those helium atoms together. There has to be an attractive force there. Remember, there are 2 kinds of forces. Kinetic, which is the force of motion, which is the energy of motion, not a force. Kinetic energy is the energy of motion. Potential energy is stored energy. When we talk about something holding atoms together, that's stored energy. That's kinetic energy stored by holding them together. And when we talk about stored energy in chemistry, we're talking about intermolecular forces. Which is one of my favorite topics. But when we talk about intermolecular forces, we are talking about non-bonding forces. These are not chemical bonds. Remember, they're, depending on how you define them, there are two kinds of chemical bonds. You have ionic and you have covalent. Now you can further and say, look, covalent can be polar or non-polar, which is important. So there's two or three types of chemical bonds. Technically two, ionic and covalent. These are the non-bonding intermolecular forces. These are the forces that hold elements and molecules together when they are not bonded together. There are three types of non-bonding intermolecular forces. Okay. There are three of them. My book mentions two of them, which ticks me off because there are three non-bonding intermolecular forces. And I keep saying non-bonding because one of them is very, very, very poorly named. We're going to start with the second one. Why in the heck would we start with the second one? It is the second strongest non-bonding intermolecular force. We start with it because it is the easiest to understand. So let's make the list. Just so we have it down. The weakest intermolecular force actually has several different names. It is sometimes called London forces. It is sometimes called dispersion forces. Sometimes it is called a van der Waals force. They all mean the same thing. So whatever your book uses, that is fine. And yes, there are two A's there. So the first one is London forces. I'm going to use the term London force. The second strongest, dipole-dipole. That's one we're going to start with. In essence, all of these are electrostatic attractions. At the core of each and every one of them, they are electrostatic in nature. That's why dipole-dipole is the easiest to understand, but it is the second strongest intermolecular force. I keep saying these are non-bonding forces. There is a reason for that. You may be getting annoyed with me. You wouldn't be the first. But I mention that because the third one has an unfortunate name. The third one is called hydrogen bonding. Hydrogen bonding is not a chemical bond. It is not a chemical bond. It is a non-bonding intermolecular force. That's why I keep repeating that over and over and over again. So let's look at dipole-dipole. All right. You have dipole-dipole intermolecular forces anytime you have a polar compound. Has to be a compound, cannot be an element. It's for polar compounds. That's when my drinking problem began. So for example, I should look up my you know what? Yeah, I need to find my. I apologize. I need to look up my Pauling electronegativity scale. I need electronegativities. Now, we talked last time about how to figure out if you have a polar molecule or not. To have a polar molecule, you must have at least one polar bond. But you cannot have a highly symmetrical molecule. That's the key. There it is. Page 82. On my book, it's page 82. If you want to play along, find Pauling electronegativity scale. So, for example, let's look at methylene chloride. Methylene chloride used to be what they used for dry cleaning. It's a wonderful little solvent. They don't use it anymore because it was killing people, by the way. Anytime you have a organic chloride compound, which means you have carbon and you have chlorine, assume it's carcinogen. Most organic chlorine compounds have at least mild carcinogenic properties. So if you ever happen upon something with carbon and chlorine, treat it with respect. So we work out the Lewis dot structure and Vesper. Remember Vesper? We need the shape. Well, this is going to be a tetrahedral arrangement. Carbon is 2. Carbon has an electronegativity of 2.5. Chlorine has an electronegativity of 3.0. That is just barely polar, but it's polar. So we have a dipole, a polar bond here. It is tetrahedral, which can be highly symmetrical, but we only have 1 chlorine and 3 hydrogens. Since we do not have 4 chlorines, those dipoles do not cancel out. So we have a polar compound with chlorine on one side. We're just going to lump the CH3 together like this. And here's our dipole. Let's put a second methylene chloride next to it. How is that methylene chloride going to orient itself? Is the chlorine going to get closer to the chlorine, or is the chlorine going to want to be closer to the methyl side, the carbon side? Well, remember, that also has a partial negative chlorine, and opposites repel. I'm sorry, opposites attract. So the partial negative chlorine will not want to be next to another partial negative chlorine. The next partial negative chlorine will want to be close to the partial positive methyl group, which puts the partial positive methyl group close to this carbon. This is a dipole. This is a dipole-dipole intermolecular force, and all it is, it's the attraction of the partial negative side of one molecule. It's the opposite attract. You have a permanent dipole. It's just the attraction of the partial positive side to the partial negative side. That's all a dipole-dipole intermolecular force is. The molecules are going to want to line themselves up so that the positive is close to the negative. Okay? That, in essence, is the foundation of all of the other intermolecular forces. So do you understand that? Does that make sense to you? They're like little magnets. You're putting the positive pole and the negative pole next to each other. That's all dipole-dipole is. Does that kind of make sense? Give me a thumbs up or thumbs down. All right. Talk about London forces. London forces are a little bit harder to understand. I'm looking at the clock, and it's unfortunate. I don't think we'll have time to cover all three before the end of the lecture. Well, let's talk about London forces real quick. Suppose we have every pirate's favorite noble gas, argon. We're going to put it next to another argon. Well, think about the structure of an atom. You have a nucleus at the bottom, in the center of it, and you have these electrons. Out here. Well, both of these argons have electrons. Out here, they're not bonded together. But they both are surrounded by electrons. But electrons are negatively charged. So when we put these electrons close to these electrons, they're negatively charged, which means they're going to repel. So what happens? Well, these electrons don't like being close to these electrons, so they're still surrounding the argon. They have to protect the nucleus. That's their job. They're the sentries. But they're going to start spending a little more time on this side. Oh, they'll come around on the other side every once in a while, but really they're spending a lot more time over here. What that does is it creates a really teeny tiny little partial negative side. Just teeny tiny itty bitty, just a little partial negative side. And if there's a partial itty bitty teeny tiny little partial negative side, there's an itty bitty little teeny tiny partial positive side. So what we have is a temporary itty bitty little teeny tiny dipole. This is a temporary dipole. And I cannot stress to you just how itty bitty teeny tiny this is. But now we have a partial positive side here. Well, the sentries of this argon are going to be attracted to that partial positive side. So they're going to start spending more time over here because they're trying to make up for that loss of electrons on this side. So here's just the opposite. We have an itty bitty teeny tiny little, is that an annoying little voice? Okay, let's try a different voice. So we have a teeny tiny little itty bitty negative charge. Again, teeny tiny, just real temporary. And of course, again, if we have a partial negative on that side, we have an itty bitty teeny tiny partial positive side on this side. So we have another temporary dipole. Very, very weak. Very, very temporary. but it's still akin to a dipole-dipole. It's still the attraction of positive for negative. But the difference is these are temporary dipoles, not permanent. So they are extremely weak. This is why London forces are the weakest intermolecular force. But the only requirement to have London forces is to have an element or compound with valence shell electrons. How many elements and how many compounds have valence shell electrons? All of them. They all have valence shell electrons, which means every element, every compound has London forces. That is the default. If you cannot figure out what other forces are present, they always, always, always have London forces, even helium. Now notice, in our methylene chloride, we have London forces as well. But we don't say it has London forces. It has dipole-dipole. Why? Well, it's dipole-dipole because the dipole-dipole is so much stronger than the London forces that the London forces are insignificant. Kim, do me a favor and ask me how much money I have to my name.
How much money do you have to your name?
Well, that's kind of a rude question to ask, but here, let me get out my wallet. Looks like I have about $14. Now, suppose we ask Elon Musk how much money he has to his name. Do you suppose Elon Musk is going to pull out his wallet?
No.
No. He has so much money in investments, in corporations, it doesn't matter what he has in his pants. So, does he have money in his wallet? Well, maybe not. He may actually hire some idiot to walk around with his walking around money to just follow him around. I have no idea. Yeah, he probably has money in his wallet, but he's not going to count it up to tell you how much money he has because it's insignificant. So if you have dipole-dipole, you're not going to bother mentioning that it also has London forces. Everything has London forces. Now, Kim, I'm going to leave it up to you. You want to run a few minutes over to complete hydrogen bonding, or do you want to save that for Thursday?
I can go over a little bit.
Okay. Hydrogen bonding also has dipole-dipole, but like London force, and by the way, hydrogen forces also have London forces. But again, hydrogen bonding is so much stronger than dipole-dipole that if it has hydrogen bonding, you just don't worry about the dipole-dipole. Here's hydrogen bonding. And by the way, there is an active argument amongst scientists, amongst chemists, as to whether hydrogen bonding is a unique intermolecular force or if it's just a really strong dipole-dipole. Reality is it is unique. Here's what happens. Suppose you have, suppose you have hydrogen fluoride. Let's take a simple example. Now, hydrogen fluoride is a polar molecule. So if we put another hydrogen fluoride near it, you might expect the partial positive hydrogen to be near the partial negative fluorine, and that is very true. But, and this is a big, big but, hydrogen is not attracted to the fluorine. The hydrogen is specifically attracted to the lone pair electrons on that fluorine. It's not a chemical bond. It cannot be a chemical bond. Hydrogen is its shell is full. It can't take any more electrons. Fluorine is happy. It has the full octet. It's not going to give any of them up. But remember, a lone pair of electrons is in an orbital, and an orbital is nothing but a region of electronegative space occupied by electrons. So, to have a hydrogen bond, they're real easy to recognize. To have a hydrogen bond, you must have a hydrogen directly bonded to an element that is highly electronegative. On the periodic chart, if you look this up, you will find that there are 3 elements. Those elements must have a lone pair of electrons. So hydrogen directly bonded to a very electronegative element with a lone pair of electrons. The only 3 elements that fit these criteria: nitrogen, oxygen, fluorine. Enough is enough. Enough is enough. Isn't this fun? F-O-N, fun. All right, I'm trying to give you some mnemonic devices here. So if we look at water, you have hydrogen directly bonded to oxygen. Yes, it has hydrogen bonding. If you look at methanol, these hydrogens do not undergo hydrogen bonding. Yes, they're in the molecule, and the molecule has oxygen. They are not bonded to oxygen. This one is. You have a hydrogen directly bonded to an oxygen. It is going to be hydrogen bonding. So just look for that hydrogen directly bonded to nitrogen, oxygen, and fluorine. Now, typically we have 10 minutes between 2 classes. I apologize. I've held you over for 3 minutes into that 10 minutes. I hope you have enough time to make it to your next class. Any questions before we break?
No.
Okay, we're going to come back and discuss hydrogen bonds and intermolecular forces a little bit more next time, because there are some ramifications we did not get to. But I will see you on Thursday. Thank you so much.